Okay, now what happens if I combine the two motions that we've just talked about? And that is called a conical pendulum. A conical pendulum is a special kind of pendulum that goes like this. So it looks like this, right? And so think about what's going on in this case. So there is definitely now an angle that exists here, right? So as soon as you do this and you try to move it, how do you get rid of this angle? Well, you can't. But dimensional analysis does not know how to deal with angles. So what we do instead is we start thinking about sines and cosines, right? That will lead us to the right equations. So let's do dimensional analysis in this case. Okay, so watch this, right? So you're right. If you project this onto the floor, it will get projected as a circle in 2D, which will then, if you can project it onto this screen, will become a simple harmonic motion. So this is a 3D problem with a 2D projection onto a 1D scale. Fascinating to think about, right? Okay, so now how do we deal with a problem like this? Well, what you do now is you split the coordinates. Just like you remember in class we did sigma fx and sigma fy. Anytime we had an angle or anytime we used to have a more than one axis that we were worrying about, we cannot write equations for both of them together. So you have to separate them into x and y components. So in this case also, we cannot deal with both of them together. So let's start by defining a few things. Let me say I want to call the length of the string L. And the next thing I want to define is this dotted line is like the equator on planet Earth. It's an imaginary line, right? That doesn't actually exist. And I'm going to call this big L. And then I'm going to call this line here, which again does not actually exist, but it is there to help me, and I'm going to call this R. And this angle, I'm going to call this theta. So now let's look at this triangle. So I'm going to use sines and cosines. So is L equals to small l cosine theta? And is R L sine theta? Once we have established that, and we also have established the fact that we have to now separate the periods that we want into x and y. So now we have to figure out the period along the x, what does that depend on? If this is my normal xy component, this is my x and this is my y. I cannot keep them together. And again, remember, so it's actually going in three-dimensional space. So this is one coordinate coming down, and this is a surface that goes like this. So it's coming out of the paper and going into the paper, right? That's why its projection is a circle on a 2D plane. Okay, so now let's see, what does the period depend on when it's moving only in the XZ plane? Just circle, not up and down, but just the XZ plane. So think, it cannot have gravity in it, right?
Yeah.
In that plane. So let's see along the x-axis first. Period depends on, okay, I assume it's going to depend on mass. What else? If it's moving in a circle, what else will it depend on?
Big R.
Good, radius. Yes, absolutely. It will depend on radius. And number 3, it depends on speed. The faster it goes, the less time it'll take. So I'm going to call this speed V. And the 4th thing that it depends on is, again, remember angle, but it doesn't necessarily depend on the angle theta. It depends on the angle phi. Right? Do you remember that your angle phi will be this angle as it goes around?
It's the sweep angle.
It's the sweep angle, the ones we were talking about. Again, dimension analysis can't take that into account, so I'm just going to ignore that.
It turns into a 2 pi.
Okay, now let's talk about the y-axis. So along the y-axis, the period depends on, what do you think? Now we're talking about this axis. So that's always where I start. Okay, it depends on mass. Number 2, In this coordinate, do you think it depends on L, which is the length of the string? The problem is that now that we're talking about, just like when we were doing mg sine thetas and cosine thetas, we cannot use L.
Yeah, I was gonna say it depends on the big L though. Right?
Yes, it now depends on the component of L in the axes that we're talking about, right? So it depends on big L. And number 3, it depends on G. So now let's do dimension analysis. X-axis. So x-axis period should depend on M, R, and V. And along the y-axis, period is a function of M, L, and G. Again, we'll do the alpha, beta, gammas.
Yeah.
Alpha, beta, gamma, alpha, beta, gamma. It's the same repeated. Beta plus gamma and T minus gamma. Now if we compare coefficients or equate powers, M equals alpha, 0 equals beta plus gamma, and T, we will get 1 equals minus gamma. Which gives me gamma equals minus 1, beta equals 1, alpha equals 0. Does this remind you of something?
By L over B.
Yes.
So we have over here.
So we will get m to the power 0, r to the power 1, and v to the power minus 1, which is the same thing as we got for centripetal force. Right? It's so fascinating. We've just reduced this down to a system of just
So
a
is the
ball moving in a circle.
I just erased it over.
And it'll just pop up. Honestly, like you'll be like, whoa, how did that happen? And I stubbornly put M's every time, even though I know they're not gonna, I don't know why I do that to myself, but I always put M there. I think part of that, the reason why I do M's all the time is because I want to make sure that I have accounted for all M, L, and T.
Just in case.
And just in case, you know, because I know that it will take care of itself, but I still want to put it in. This will just be 0 equals alpha and 0 equals beta plus gamma, and 1 equals minus 2 gamma, which gives me gamma as minus a half, and beta as a half, and alpha as a. And what do I get at the end? T is proportional to m to the 0, L to the half, and G to the minus half, which means I can write this as T is proportional to L over G. But did I not say L was L cosine theta? So then that means I can rewrite this as L cosine theta over G. Which, if you were to think about, what is cosine of 0?
1.
1. So what if your cosine, do you remember what your cosine angle actually was? It was this angle at the top, right?
Yeah.
If theta becomes 0, what does this equation reduce down to?
Or 1 over G. Or L over G.
So if theta becomes 0, then cosine of theta becomes 1, And what does this equation reduce down to?
Root L over G.
Which was the same equation as that of a
What was that?
simple
Yeah,
pendulum.
it was a simple pendulum.
Yep. So basically, a conical pendulum is a simple pendulum plus a centripetal motion.